Hello, my name is Victor Mwai. I'll be taking you through introduction to networking. So a little about me. I am Victor Mwai. I play CTFs with perfect truth, and I'm a fourth year student in Jomo Kenyatta pursuing computer technology. And I do blog about security and other related topics. There is my link, and then Twitter and my LinkedIn handles are as shown below. So agenda for our discussion today will be introduction to networking, the three-way handshake, and then you learn about the OSI and the TCP model, and then importance of networking in cybersecurity, and there will be more on protocols, subnetting, and more. So a brief introduction to networking. So we all know the world is now a connected village, or rather small village, connected by the power of networking. A good example is the way we are communicating right now. You guys maybe are in Tanzania, some are in Kenya, but through the internet and networking, we can be able to communicate online via Zoom, Google Meet, many other ways, etc., etc. So a brief introduction of what networking is. What a network is. Network is a collection of interconnected devices that communicate and share resources with each other. These connections are established through wired or wireless communication channels. So example of these devices could be computers, servers, smartphones or IoT devices, Internet of Things, like CCTV cameras, sensors, and many more. So a brief importance of networking. So it helps in identifying the scope for penetration testing. This is a good example for pen testers that, let's say you are going to an organization, you have been tasked with the task of doing security assessment for the company. So you'll be given a document that contains IP addresses for the network of the entire organization. Then you're told you'll not touch this subnet, but you'll perform your assessments on this subnet. You see? So through networking, you'll be able to understand, okay, I'm not supposed to touch this certain number of IPs, but I'm allowed to touch this certain number of IPs. And then it helps in designing secure network architectures. This is a good example for network engineers that are trying to design a secure network for an organization, let's say like Hackit. Yeah. And then it helps in network monitoring and threat detection. This is a good example where this is usually seen by the SOC analyst, Security Operations Center analyst, that monitor the organization's network for threats or even malicious or anomaly behaviors in the network. And then another importance is incident response. By incident response, to understand it, I could use an example. Let's say an organization has been attacked by a ransomware. Yeah. So through networking, one can be able to identify devices that have been affected first by the ransomware attack by identifying their IPs. By IP, it's you could think of it like a identification number. Like here in Kenya, we Kenyan citizens have been given an ID card that contains your number that uniquely identifies you in the country Kenya from other citizens. Yeah. And then some examples, we have the local area network. This is a small network within a small geographical area, such as a home, a school, or an office building. Think of it like your home having a Wi-Fi network. Wi-Fi network, you have a router, you have laptops, smartphones. So the router functions as the gateway to your network. That is gateway meaning from your laptop on in your house, you can communicate to the World Wide Web through the router by sending out your traffic through it. And then we have the metropolitan area network. So it's a computer network that connects computers within a metropolitan area, such as a single large city, multiple towns, or any large area with multiple buildings. Think of it like Dar es Salaam, a city like Dar es Salaam. You have different buildings within the vicinity. So these buildings could be connected to each other for communication through networking. That's what we call the metropolitan area network, where the buildings have each have their own LAN, So when these LANs get to be combined together, they form the metropolitan area network within Dar es Salaam. We have a wide area network, a computer network that covers a large geographical area comprising a region, a country, or a continent. Think of it like the continent Africa. We have undersea internet cables that enable African continents to connect to the internet and communicate with other people outside the continent of Africa, let's say in America, South America, and many other places. Yeah. We have a wireless local area network. This is a wireless network that allows two or more devices to be wirelessly connected. You see, to be wirelessly connected to form a local area network or on a limited scale. A good example, just as I have explained earlier, your home network. You have a Wi-Fi, yeah. In your Wi-Fi, you have routers and many other things connected in the network. And then you have a personal area network. It's a computer network that is used for data transmission between different personal devices such as computers, cell phones, and digital devices. You could think of a personal area network like your own laptop. Through your laptop, you will be having it connected to a network, and then your laptop can serve as two gadgets, either as a client to the network, or it can also serve as an access point by you turning on your hotspot on the laptop for other devices on the network to communicate with each other. Now we'll go next and see how this communication is usually done. So for a TCP connection to be done, from the definition we saw earlier of a network, where we said it's a what? It's established through wired or wireless communication. Now, what is happening here, for a wired communication to be established, a three-way handshake has to take place, whereby we have a TCP client and a TCP server. So I'll break it down by using a simple example. Let's say the TCP client is me, Victor, and then the TCP server is Karim. Victor wants to communicate to Karim. So Victor starts by saying, "Hello Karim, how are you?" That's a synchronization packet I've sent from the TCP client to the TCP server. Now from the TCP server, who is Karim, Karim will reply back, "Hello Victor, I'm good. How about you?" So the TCP server has sent a synchronization acknowledgement packet, a SYNACK packet, back to the TCP client to say, "Okay, I've acknowledged you. Let's continue the communication." So Victor now will continue the communication with Karim. Okay, Victor wanted to ask Karim if he could join the cohort 9 or the cohort 3 bootcamp. So Victor says, "I would love to join the cohort 3 bootcamp to kickstart my career in cybersecurity." Yeah, and then from there the communication goes on and on and on. So the three-way handshake is usually essential in establishing the fast communication between the TCP client and the TCP server, just as I've explained here briefly. So the TCP client initiates the connection by sending a SYN packet to the TCP server, and then the TCP server responds with a SYNACK packet, and then the TCP client then sends an ACK back to the server, and the communication goes on forth and forth. So for a simpler example, let's do it using Wireshark. So we turn on our where we are connected and connect to the Wi-Fi. So we'll start our capture, and then I'll go to my web browser and visit, let's say we visit google.com. You see, we have visited google.com. Wait for it to complete rendering the page, and our page has been rendered. So we close it and then we go back to Wireshark. We stop the capture. Now we'll have to filter this communication in order to identify the SYN packets. I mean the three-way handshake. Let's filter. We have many: quick, DNS, TCP, TLS. Let's filter all these protocols so we can say not ARP. ARP is a protocol. I will explain to you later on. And not ICMP. ICMP is also another protocol. And not DNS. Let's see what we'll get. The demo gods have decided to do me dirty. Okay, let's continue filtering and not TLS. TLS also we have filtered it. Let's see if we have another. Not quick. Not quick. We want to filter it so that we can get it. 3-way handshake. Is that? Why am I not seeing my Synac? Arc. Just in acknowledge. Okay, let's try capturing differently. Don't save. Let's visit another page. Let's visit my blog page. So you can try let it render. Visit my blog page. There are some of the blogs. Wait for it to finish to render. It was finished rendering, isn't it? So we close the page. We come here and then we terminate the capture. Okay, now let's try again. I hope right now we can be able to filter. Let's just filter for TCP. TCP we have seen in bingo. Here we have. So see from my IP, I have sent a synchronization packet. The web server has been identified that is serving my web page. So my IP through port 55447. You could think of a port like one door among many in your house. Let's say maybe it's a door to my room. So from my door, I want to go outside my room and then I go to the door that leads me outside my house. So this is another port 443. So port 443, it's the port that it's serving my web page on this IP. And port 443, it's a common port, commonly known as HTTPS. It's a secure version of HTTP. So a synchronization packet has been sent, and then afterwards, the server communicates back by sending what? A SYNAC. Now from my server, it communicates back to me from the port where it was serving my web page, port 443, as you can see, to my port where I was communicating to the web server through it, port 55447. After it has established the SYNAC, then I send back an acknowledgement saying, okay, the page I've seen it, now render it on my browser. It gets rendered, see, back to my browser as we saw earlier. You can see TLS. TLS, it's an encryption protocol for HTTPS. We have TLS and SSL. We'll come to know about it. So we have a TLS certificate in my web page. That is just a brief summary. So from SYNAC, and then ACK. So this was to show you how the communication takes place. We have a synchronization from the client, and then the server sends back a SYNAC, then the client sends an ACK. and communication is established, and from there communication goes on and on and on between the client and the web server. I guess that is quite clear now. So we can continue the slides. So we've been able to understand the three-way handshake, the OSI model. I guess we can jump a little. I will come to this OSI model and the TCP/IP model later on. Let's go to protocols so that you can be able to understand what I was saying while in Wireshark. We could go to my notes where I did some research. Let's go to some protocols. We have some common protocols. We could start by defining what TCP, UDP is, MAC addresses, and the protocol in layman's language, as I've explained here in the slides. What it is, it's a set of rules that govern communication between devices. Now, from my command prompt, we can start by identifying. So we have commands that usually outline network details of devices. For an Windows machine, we use ipconfig. This is for Windows, and for Linux is if config. Linux and Mac OS if config. So we could do if config so slash all. So what I've done here, I've said if config slash all, or slash all, it will show, how can I say, the network details for all the interface cards in my device recursively from their MAC addresses, IP address, IPv4 and IPv6, and many more. Boom. So we have. So currently I'm connected to my Wi-Fi, and you can see there is a lot of details just from running the IP config, and there are many other network what we call. So this is my network interface card, my wireless interface card in my laptop. We have an Ethernet card for VMware adapter because I have VMware and I have some virtual machines running, but at the moment they are closed, they're shut down. I mean, we have a wireless adapter and many more, but we are currently interested at this, the one we are connected to, the wireless LAN adapter Wi-Fi. So we have some details here. We have a physical address. Physical address, it's in other words, it's called the MAC address. We have DHCP. DHCP is another protocol that enables the dynamic assignment of IPs in a network. It's dynamic host configuration protocol. So through DHCP, my laptop has been assigned an IP address, as you can see here. This was done randomly, as you see, preferred. So meaning there are many other IPs in the network, but I assigned this IPv4 address, and we also have an IPv6 address and a subnet mask. A subnet mask, think of it like uh, let's say Hackett organization. It has different departments, yeah. So my IPv4 address, this IP is in this subnet mask, and this subnet mask in layman's it's /24. By /24 I mean this first, it's a decimal notation of our subnet mask, which is /24. And by decimal notation, it's a data representation of computer data. Uh, what am I saying? Ha. Decimal notation, I mean, it's the representation of data in decimal format from using numbers ranging from 0 through 9. So, yes, for 0 through 9, that's for decimal notation. This is decimal notation. And then what I was to show you now, it's a binary notation representation of 2555. And for binary notation, is the representation of data in numbers ranging from 0 through 1. Yeah. And then the IPv6 that you saw here earlier here, this one, it's represented in a hexadecimal notation. with numbers ranging from 0 through 9 and letters ranging from A through F. Okay, so that's just a small what is happening, small representation of these datas. So 255 in binary notation, it's 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. 8 ones. That's for 255. What is happening here? Data in computer, it's represented in terms of bytes. And 1 byte is made up of 8 bits. It's made up of 8 bits. Okay? As you can see, this 255, this is 1 byte, and it's made up of how many bits? 8. 8 ones. This is the decimal notation for 255. Not decimal, but binary, I mean. So 255, 255. So the one we have, it's how many? We have how many octets? 3. 1, 2, 3. So another 8. 1, 2, 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8. And then the 0. 1, 2, 3, 4, 5, 6, 7, 8. So by me saying it's slash 24, what it simply does, what I simply mean, it's this one, this is 8, this is another 8 bits, this is another 8 bits. So what I've done, it's 8 times 3, because we have 8 bits per 3, 8 bits per octet, and in our case we have 3 octets. So it's 8 by 3, which is 24. And, the the IP address that you're seeing here, it has many details under it. So from 192.168.100, this first part is the network portion, and then this is the host portion or the node portion. So for slash 24, we have these 3 parts. The first 3 octets as the host portion. You could change it to slash 25, slash 26, on and on and on. And the host portion will, I mean, the network portion will keep on changing, determining on the subnet mask used. So in our case, it's slash 24, meaning this is our host portion, I mean, our network portion, and this is our host portion. Yeah. So I will go to my notes and explain further what we have here. So IPv4 is made up of 32 bits. By 32 bits, we mean it's 8 bits, because we saw each octet has 8 bits multiplied by 4. That's how 32 bits comes into the picture. So the first 3 octet usually represent the network portion. That is for subnet mask 24, as I've shown you in the example we had in my command prompt. And then the last octet is the host portion. So I could put it in this way. So this is 192.168.100. That's our host portion, and then I mean our network portion, and then the .40 that we saw in our command prompt is our host portion. And then, so in the current world, IPv4 it's getting depleted, with many devices being created and being connected to the internet. We have robots, IoT devices coming up, new inventions day in, day out. So we have initially, we had, not initially, even now, we have network address translation protocol, also known as NAT in short. And this helps in the depletion of IPv4 address by allowing multiple devices on a private network to share a single IP address. So a good example of this, we could say we have an apartment of, let's say, containing how many tenants? 30 tenants. In this apartment, we contact our ISP provider because we want to give our tenants internet access. So from our ISP provider, we will be given one public IP address. Let's say from this table that I've shown you up here, We could say we have been given a public address of 192.160.0.1 as an example. Now, from this public IP address, we will now take it and do some subnetting into it and divide it further into different subnets that our employees, or rather our tenants in our apartment, can use. That's what NAT helps in doing. A device is given one public address, let's say our router, and then from this router we do subnetting that will have more or smaller private subnetworks that our tenants can be able to connect to the internet through it. Okay, so that's IPv4. Now we can go to IPv6. Just the same breakdown that I had earlier, I will now give you using another example here. So this IPv6 address structure, as you can see, we have the first 64 bits, the network part, and the last 64 bits as the node part. Now, as I showed you earlier in our command prompt, 255, its binary notation is 8 ones, 1, 2, 3, 4, 5, 6, 7, 8. Now, when it comes to IPv6, let's say the 201, 2001, this first octet labeled here, is represented using 16 bits. Okay, so from this breakdown, the first 64 bits, it means how many? The first four octets, each made up of 16 bits. So it will be, so 64 comes in by doing 16 multiplied by 4. That's how it becomes to 64 bits. So each octet, this one octet has 16 bits, this other octet has another 16 bits, this one 16 bits, and the same goes for the rest. This is for the normal IPv6 address like the one we have been assigned in our network through DHCP, like this one. The first 16 bits, the first four octets are usually for IPv6, I mean network portion, network part, and then the last 64 bits, the host portion. Yeah. This second one that you're seeing here down, it's for a broadcast address. A broadcast address, this is a type of address whereby, let's say in my network, yeah, through my laptop, there's another device in the network, but it's not known. Rather, its details are not in a switch because our switch contains what we call an IP table, where this IP table is assigned, rather, it's filled with IP addresses and their MAC addresses in the network. But the device I want to communicate with, it's not in my network, neither has it been identified on the network. No, from my laptop, I will send out a broadcast address, and this broadcast address, what happens is, from my laptop, I send a communication. Let's say, I say, "Hello, I'm looking for." You could say our message is, "Hello, I'm looking for Karim." Karim is not in my network, yeah. So this message will originate from my laptop, yeah. Then it will be broadcasted to all other devices in the network. Now, the device that will identify itself as Karim will communicate back to me. And when it communicates back to me, its IP address and its MAC address will be updated in the IP table of the switch, and then it will get to be identified. And this IP address will be mapped to its MAC address by the ARP protocol, address resolution protocol, will be able to map this IP address to its MAC address. And if the IP address was not identified, rather the MAC address is identified, a reverse will happen, what we call ARP, reverse address resolution protocol, where the MAC address now will be mapped to the IP address of Karim. Okay, and then communication will go on after they have identified each other. And this is a breakdown of the IPv6 broadcast address. So we have the first 48 bits. The first 48, we could say it's how many? Which we could say it's the first three octets. Yes, because 16 times 3, 18. Yes, the first three octets here will be identified as what? Then unicast address, and then this one will be identified as the subnet ID, and then the last three will be identified as what? In these two here, these four will be identified as the 60, the host portion of the interface ID. In other words, so what is a MAC address? From our command prompt, we have been given a physical address. This is another name for MAC address. It is also referred to as hardware address, physical and band-in address or Ethernet address. And what happens? The first three usually resemble the OUI, the organizationally unique identifier, while the last three, or the last 24 bits, are unique to the specific device within the manufacturer's range. So you could say, let's say for ours, it's 50, and it's saying the description is Intel R Wi-Fi this. We could do a MAC lookup of this. Let's go and check it out. And MAC addresses can be represented in two ways. As the one I've, like this. This is the first way, and the second way, it's like this. Okay, using the hyphens between the digits. You could do a MAC lookup, MAC address lookup. Let's do MAC address lookup. Oh, I did it earlier on. Okay, let's click here and search and see what will identify about this MAC address. Boom, we have our company identified, it's Intel Corporate. We have the company address and many more, many more. Just from the MAC address, we are able to identify the laptop was made by Intel. These first three portions, it shows the Intel, and this one is the the identification number of our Wi-Fi adapter in our laptop. Okay, yeah, and that's it for MAC address. But however, there is an attack that usually happens, what we call impersonation attack. For MAC address, it's done through what we call MAC spoofing. In Linux, there is a tool called MAC changer. This tool helps in impersonating or changing our MAC address. And the syntax you could use is, let's say for Linux, if you run it on Linux, you could say MAC changer TAC-R. So TAC-R will randomize our MAC changing. So let's say we identified this is our MAC address. Okay, you could do this TAC-R and then V, but we have to specify the adapter we want to change its MAC address. We could say it's 0 or any other. In our case, let's say we want to change the MAC address for which Ethernet adapter. We could even change for this wireless interface card, but on Linux. So this is a syntax. So you say MAC changer, TAC-R for randomization, and then the adapter you want to change the MAC address for. And for it to function well, you can run it. We usually run it with the root privileges. Okay, yeah. So as I just stated earlier, we have the app protocol. So what app protocol does, it maps IP addresses to MAC addresses, and the vice versa for each is a RAP or reverse address resolution protocol that maps the MAC address back to its IP address. I guess that's it's clear from what I had explained earlier. Then another protocol is the TCP and UDP protocol. These are layer 4 protocols, which is the transport layer. And then TCP in full is transmission control protocol, and UDP it's user datagram protocol. They have some differences. TCP is connection oriented, while UDP is connectionless oriented, meaning UDP can transmit packets without being checked for errors, unlike for UDP. However, UDP is faster than TCP, but the only disadvantage that it has, as I've stated here, it does not provide error checking or flow control like for TCP. It is connection based, as I have stated earlier. And then from the example, for communication to be established, a three-way handshake has to be established first so that communication can go on. Yeah, and then we have the UDP. It's faster and reliable compared to TCP. Because let's say I give you an example. Have you ever wondered using VoIP, voice over internet? This it's called VoIP. It's another protocol that is used for landline phones. These are what I mean by VoIP. I guess we have all come across these kind of devices, maybe in an office or somewhere. So these they use the VoIP protocol. You could communicate with someone easily. However, the packets are not usually most of the time sent in full. They're usually broken down, and you could say the first portion of the packet has been sent over, the others have not yet been sent over, and still the communication can take place. Unlike for TCP, the entire packet has to be encapsulated fully from the first layer, physical layer, up to the last, which is the application layer. Each layer has its own data encapsulated into the packet as you go from one layer to the other, and like that and like that. So when this packet reaches to the destination, it gets decapsulated. So each data in each layer it gets to be decrypted from the application layer all the way to the physical layer, and then the communication continues like that. Okay, and then we have other common ports. FTP, short form for file transfer protocol. It runs on port 21, and Secure Shell. This is a secure version of accessing servers remotely for Telnet. Telnet is the unsecure version of SSH. SSH runs on port 22, while Telnet runs on port 23. SMTP is the protocol used for email communications, and it runs on port 25. SMTP runs on the server side. Just the same way you saw we have TCP client and TCP server, we usually have an email client and an email server. SMTP most of the time you'll find it runs on the server side. Okay, SMTP. Let me put, it keeps escaping my head. SMTP in full. It means Simple Mail Transfer Protocol. It's a fundamental protocol used for sending and receiving emails over a network, including the internet. Could see images of how it does. Oh, we usually, okay, we even have an SMTP client and server, as I've stated earlier. So we see POP3 and IMAP, SMTP. There is another, SMTP also has its own technologies for you to understand how it runs. Then we have domain name system. So this is the protocol that helps in mapping uh, human readable domain names into IP addresses. For instance, we could say we all know what Google.com is a domain by Google, but we want to know the IP behind it. So we could use a tool like NSLOOKUP it's able to map, or rather get the IP of this domain. So let's look up, and here we go. The IP address behind google.com is 172.217.170.206. So this was made able through DNS resolution. So what happens here? It's like this. So if we search on our URL, google.com, you see it loads. While it's loading, the DNS gets to identify, okay, google.com, what's google.com? It will check its, in my device, it will check the DNS cache. DNS cache is, it's like a table that contains a temporary memory of DNS names that have been mapped to the IP addresses. If it will check the DNS cache first to see, do we have google.com in our DNS cache? It will go through the DNS cache, finds it, and then the page gets rendered in our browser. Otherwise, if it doesn't have the DNS cache, the DNS cache doesn't have our domain, the domain will be sent out to the internet. The DNS protocol will then try to map it to the IP and then communicate back to us and then render the page on our web browser, as you see here. That's the DNS protocol for you. And then we have hypertext transfer protocol. This is the secure version of transferring or rather rendering web pages on the browser. So HTTP it's unsecure, and here you can even transfer uh, data in plain text. By data I mean you could transfer credentials in plain text over the internet and get hacked, or the data gets to be stolen by malicious actors. While HTTPS, now it's the secure version of HTTP and it runs on port 443, as I showed you earlier in the Wireshark example. POP3 and IMAP, these are protocols used by mail clients like Outlook and Gmail. And POP3 runs on port 110, while IMAP runs on port 143. SMB, just like FTP, is also used for file sharing. And SMB in the recent days it's mostly used in Active Directory environments for file sharing, and it runs on either port 139 and port 445. Port 445 is the new version port for SMB, and these are the ones that run under the TCP protocol, connection oriented protocols, that is. But DNS has also a connectionless oriented protocol that runs under UDP. And then under UDP, we have DHCP that runs on either port 67 or port 68. And DHCP is the Dynamic Host Configuration Protocol, just as I showed you earlier here in our network details slash all. We are connected. So through DHCP, we are assigned an IP address automatically and dynamically in the network. So this IP that we have been assigned here right now, when we switch off our device, this IP will be taken by the DHCP again. When another device connects back to our network, it may be given the same IP or a new one. Okay. Now, uh, to explain more on TFTP, Trivial File Transfer Protocol, it's the same just as FTP, but it's less complex than FTP, and it runs on port 69. Also SNMP, it's another protocol. Sorry, SNMP here. It's a protocol for device management. And by device management, by I mean troubleshooting. SNMP protocol. Search and see what it is about. It's a simple network management protocol. It's a widely used standardized protocol for managing and monitoring network devices. Okay, and we have some key features which you could go and read further. I was just giving an overview of the protocols. And then sometimes you might find that HTTP it's not running in the required port, as we all know, port 80 in a company. You could find it's running on either port 10,000 or another port, the same to SSH and many more. For this, what is happening is something we call security obfuscation, security through obfuscation, and this helps in making it harder for attackers to identify vulnerabilities, more difficult for the attackers because when an attacker wants to attack an organization's network, what it does first is by scanning the IPs to identify which services are running on which port. You see, HTTP is a service that runs on port 80. And for security obfuscation, I mean rather, we change our port, which is port 80, and we say, hey, let HTTP be running on port 10,000. An attacker, after he has done the scans and then he finds out that HTTP runs on port 10,000, he will be one shocked if he's not patient enough to do further analysis and then stop. Others may continue to find, okay, it's running on port 10,000. You will go and see this page, what it's hosting. You could find maybe our IT guy decides to be lazy and uses an Apache server that is way older with vulnerabilities. But through obfuscation, it was quite hard for the attacker to identify easily rather. Yeah, that's all about the protocols. Now we can go to the OSI model that I had explained earlier here. Okay, the OSI model has 7 layers, as I stated earlier. And then I will say how it works. We have physical layer, data link, network layer, transport layer, session layer, presentation, and application. Sometimes it's difficult to remember all of these layers in their order, but I have a mnemonic that I usually use. Please do not throw sausage pizza. Please do not throw sausage pizza away. The first one, please, the physical layer. Do, data link layer. Not, network layer. Throw, transport layer. Sausage, session layer. Pizza, presentation layer. Away, the application layer. And many more. So in our slides, the physical layer, this is where it's a connection-based layer. Rather, here is where we have find the devices, coaxial cable, the Ethernet, fiber optic, etc., etc. So here the data bits are transmitted in raw bits. Data is transmitted in raw bits and digital signals. Raw bits over the physical medium. That is digital signals into analog signal and vice versa. So here it's mostly in electrical signals because wires understand data transmission through electrical signals. But in the case of fiber optic, it's through light. And then the raw bits from the physical layer get to be organized into frames on the data link layer and then defines the format of data on the network. So the raw bits here gets to be defined into frames when they reach the data link layer. So here the first encapsulation takes place. The bits get converted into frames. Rather, the bits from the physical layer, when they reach the data link layer, they are organized into frames. And then from the data link layer now, when the frames reach the network layer, more data is inputted, rather, it's embedded into the packet. We could have the source IP and destination IP, source port, destination port. Here on the network layer, that data will be encapsulated in the packet. And then this packet then gets transmitted to the transport layer, where it will be determined to be transported either through TCP protocol or the UDP protocol, which will get be encapsulated on the packet. You see, from physical layer up to now, our packet it's getting built slowly by slowly by slowly. After the transport layer, the session layer now, yeah, what happens, you could think of it like, let's say you're going to a hospital, you want to visit a doctor, right? Outside the doctor's door, we have patients lining up to go and visit the doctor. So after every patient's time with the doctor ends, he leaves the office, right? Now, in our case of a network, every device on the network that it's connected, its session is durable up to the time when the device gets switched off or disconnects from the network. Sorry, gets switched off or disconnected from the network. And from here on the session layer, what happens? We manage and terminate sessions, and then synchronization data transfer with checkpoints. So checkpoints are then added to our packet at the session layer. And then from the session layer, our packet gets either encrypted or decrypted in terms of reaching the destination, but encrypted in terms of from the client source destination, that is. And then if you have big files, they get compressed, and then these big files will be decompressed on the destination side or on the receiver side. Now, that from the physical layer to the presentation layer, our packet gets encrypted. Now, the application layer, this is where we provide a user interface where application can access the network services. Think of it like me as the source. I want to send a file out, let's say to Karim. So what happens? My file, it's broken down into bits, frames, encapsulated up to this presentation layer where it gets compressed and encrypted. And then application layer, we could do a file transfer using a protocol, or rather a service like, let's say, Megabox, or Dropbox. Dropbox will then transfer I'll provide Karim with a link to my Dropbox where he'll be able to access the file. Now, on Karim's side, what happens? This file, he will unzip it. Maybe I had encrypted it using a password. I will give him, okay, here's the link to my Dropbox with the files. Decrypt it using this key. After he has decrypted it, the vice versa happens. Decapsulation. The file gets broken down into all the data, let's say the data units for each layer up to the raw bits. The raw bits is the language that computers understand, the zeros and ones. The computer will understand the file. Yeah, that's what happens in the OSI model. That's just a brief breakdown of it. And the TCP/IP model is the summarization of the OSI model, where you can see here the data link layer and the physical layer will be combined to form the network access layer, while the application layer for the TCP/IP, it's combination of the session, presentation, and application layer combined to form the application layer alone. This is just a complementary of the OSI model. Then from the protocols, this is the OSI with summarization of the protocols on each layer. As I said, transport has TCP, UDP. Network, we have IP, ICMP, IPsec, IGMP. So IP, Internet Protocol, I said earlier you could think of it as identification number. This is a number that uniquely identifies a citizen of Kenya from another citizen. Now for IP, it's the number that identifies one device from another. ICMP, for our case, is a protocol that is used for troubleshooting or checking if devices in a network can communicate. For instance, let's say we identified our, let's look up, google.com's IP, google.com, here's the IP. So we could try ping this IP, 170.206. So what you're seeing here, these are ICMP packets being sent to the server hosted at this IP. And the statistics are here. All packets have been sent and have been received. You have 0% loss, meaning from my device, I'm able to reach google.com's web server easily, and the communication can be established. Okay, and then the networking hardware and media. So this is the physical layer, layer one. So the transmission media, as you can see in this image, is broken down into two: guided media and unguided. So guided media is connection based, while unguided is wireless media. So this is wired media, wireless media. Sorry, not connection and connection. This is wired, guided is wired media, and guided is wireless media. On guided media, we have different type of cables. We have twisted pair, coaxial, optical, strip line, micro strip line. And here are just a few examples, but I'm quite sure some of you are familiar with these cables. Oh, and to add, the twisted pair cable can be terminated in two ways. We have the straight through and crossover. And after the termination, the cables are connected using an RJ45 that will be able to link those cables together so that they can be used for data transmission in a network. And then the unguided media, we have radio waves, microwaves, infrared. Yeah. So this one, you could say like radio waves. You have been hearing of network 4G networks, 5G networks. That is just a variation of the waves. For you could say 5G, it's way faster than 4G. We all know that, and yeah, it's just a difference of the waves, the radio waves being used for the transmission. Infrared wave, this one is commonly used in television. So your remote, for it to change a channel on the television, there's an infrared wave that is sent from the remote signal. At the end of the remote, or rather the tip of the remote, we have like a small red. Uh, it's is it a bulb? A small red bulb, and then on the television we have a red beeping, a red beep or a small lighting. If I could show you using the an image, TV and remote, infrared images. You see at the tip of the remote. So this tip over here, this tip, there is also a flipper zero. You can see. So there is an infrared signal usually sent from this tip to the television so that it can aid it in changing a channel. As you can see in this image, this remote, there's a tip here that sends out an infrared signal, and then the TV will receive it for it to be able to change a channel. Yeah. So network troubleshooting, you've seen how ping works, testing communication in a network, ipconfig, used to display and manage the network configuration. We have used ipconfig in our case for Windows to display the network details of our device. Traceroute in another case, it's a diagnostic tool used to map the path route data packets take from the source to a destination across a network. Let's say we could use traceroute. So traceroute usually shows number of hops that have taken place to reach our destination. Let's say we want to reach google.com from our device. You can see we have the first hop. So we have maximum of 30 hops. It will take some time. So in other case, you'll see number of hops over here. You see this first one, this first hop, this is my router IP address, which is also functioning as my gateway. You see? There's the second hop is timed out, then the third hop. It goes on and on and on. You could wait and you will see all of the output. Yeah, that's it. Thank you. That was my time. We'll ask questions. Oh, sorry. We didn't talk about subnetting. So, subnetting, an overview of subnetting. Yeah, okay. Process of dividing a network into smaller networks. Smaller networks. So, subnetting allows for more efficient use of IP address. Just as I said earlier, the example that we used of we have an apartment with maybe 30 tenants. We want to give all our tenants internet access. So we'll be given an IP address that will be able to do further division for smaller networks. Thank you.